I've decided that we're going to split this section 9.3 into two different videos. This one should be the shorter of the two videos. Your assignment is just to watch the two videos for the week. Next week, you'll do all the work for them. So this should be a pretty easy week in terms of what I'm asking you to do. For this first video, we're just looking at two things that, two new statistics that we can use to look at quantitative bivariate data, which is what you've been doing, the scatter plots, XY stuff. And we have the coefficient determination and the standard error of the estimate, or the standard deviation residuals. So we're going to start with the coefficient determination. The coefficient determination is symbolized as r squared. All right, so it is r squared. Notice the capital R, that's just what usually people do. But that's the symbol for it. And ironically enough, it is actually equal to little r squared. So the coefficient determination is literally just squaring the correlation. So that's why I said r squared equals r squared. So if you take the correlation and you square it, you have the coefficient of determination. So like that, it is just the square root of the correlate, or it is the correlation squared. So if you don't have r squared already given to you, if you have a correlation, you can square that. Also, we have a correlation calculator. If we need to find r squared, we can use that calculator and then just square our answer, and you have r squared. The more important thing is, what does r squared mean? Let me give you the definition of that. R squared is the percent of the variation in y that is explained by the linear relationship with x. So what does that mean? It's how much variability there is that's actually accounted for by the model. So you know that when you have a linear relationship, it's not ever going to be perfect. It's never going to, not every point's going to fall in the line. And r squared is telling you how much of that variability, those points being from the line, it's just part of the model. It's just the way it is. But ultimately, you just need to remember that sentence. So it's the percent of the variability or variation, same thing, and y that's explained by the linear relationship with x. And we'll go over how to do that. Well, we'll do, I think, 3 examples, so there should be no question about how to do that when we're done with the video. And then we have the standard deviation of the residuals. That's usually what you see. Standard error of the estimate, same idea. Just different words. A lot of people call them different things, but I usually say the standard deviation of residuals. It is denoted, it's denoted as S. Usually you'll just see S. Sometimes you'll see SE, standard error. But usually it's just S. And we'll look at multiple examples of that, how you find it. Now, the good thing is you do not ever need to calculate this by hand. It's too tedious and annoying to do, so you'll never have to do that. It'll always be given to you. Your job is to find it and to interpret it. So the interpretation for standard deviation of the residuals is the average distance, the actual y values are from the predicted y values. So let's draw a picture of this again. If you have your scatter plot, something like this. The idea here is if you measure how far each of these dots are, okay, let me just make them far away. If you were to measure how far each of these lines were, or these dots were from the line, and then averaged it, that is what S is. It's the average distance those real dots are. Remember, those are real data values from the predicted line. So the smaller it is, the more precise the line seems to be at predicting. The bigger it is, the farther those points are, and the line is not doing maybe the best job at predicting. So these are the two ideas that we're talking about in this video. The coefficient of determination, or R squared, and the standard deviation of the residuals, which is usually S. So let's take a look at our first example here where they're just listed. So it says the correlation coefficient for the gross domestic product and carbon dioxide emissions data that we've been looking at is 0.912, and the standard error was 12.183. So they call it the standard error rather than standard deviation. We want to find the coefficient of determination, which is R squared. Excuse me, and we're going to interpret the coefficient of determination and the standard deviation of residuals in context. Okay. So the first problem we have is we don't have R squared. We have R. So in order to get R squared, we literally need to do R squared, which is going to be 0.912 squared. So we need to figure out what that is. So if we go to our trusty calculator, and we get 0.832. So R squared we have as 0.832. R squared, though, is always written as a percentage. So when we do our interpretation, I'm going to convert that to a percent, which is why I wrote percent of the variation right here, because it needs to be a percentage. So if we do that, first the percent of the variation in y that's explained by the linear relationship with x. So if we convert this to a percent, it's going to be 83.2% of the variation. It could also be variability. You don't have to write both, but just be aware both are okay. Of y. Now, if I recall, the carbon dioxide emissions is y. We were using GDP to predict the carbon dioxide emissions. So when we say of y, we need to actually list the y variable. So 83.2% of the variation in or of carbon dioxide emissions is explained by the linear relationship with x, but same thing. We don't want to write x, we want to write what x is. So x in our case is gross domestic product or GDP. So 83.2% of the variation of carbon dioxide emissions is explained by the linear relationship with GDP. And you just interpreted R squared, the coefficient of determination. It's that simple. You just plug in those three parts into your little sentence that you can look at, and you're done. So now we want to interpret S. So S is right here, the standard error or the standard deviation of residuals, whatever. So we have 12.183. Now recall standard deviation retains units. So if you do have units, you want to include them with this interpretation. I take that back. So we're not going to list the units. Well, yeah, we'll list the units. Okay, so we'll list the units. Sorry, just had a little thought there. So to interpret this, if we go back, we have the average distance the actual y values are from the predicted y values. And then we're going to write is blank. Okay, so if we're going to do that, we would write the average distance, the actual carbon, remember our y is carbon dioxide emissions, oh goodness, okay, dioxide, okay, there we go. All right, the average distance the actual carbon dioxide emissions are from the predicted carbon dioxide emissions is 12.183, and I don't remember what the units were. I don't remember what your units, and they're not listed what that unit was, so I'm just going to write that. So the average distance the actual y's are from the predicted y's is 12.183, or the average distance the actual carbon dioxide emissions are from the predicted carbon dioxide emissions is 12.183. That's it. That is what this video is about. It is about just interpreting these two statistics. All right, now usually they're not just going to be listed for you, they're actually going to be hidden in a way in our computer output that we looked at briefly, but we haven't spent a ton of time with. So next example, we're going to ignore the directions because the next video we're going to use the exact same thing here and we'll actually do what it says. But this is a lot of times you have that big table and we need to be able to pull them out from this table. So apparently in this study, a random sample of service call records for computer repair operation were examined, and the length of each call in minutes and the number of components repaired or replaced or recorded. So once again, just ignore the directions right now. We're not going to do that in this video. I'll do the next video. So we need to find, I want to interpret R square and S. So we can find them. Now we have R squared right here. It says R squared and it says 98.7%. Now you'll notice right next to it we have R squared adjusted. That's there to mess you up. So don't ever pick that. R squared adjusted is nothing we're ever going to deal with. Don't worry about what it is. It doesn't matter. So ignore that. So R squared is usually listed as written as R squared, or you'll actually see R with a little 2 on top of it. And the standard deviation of the residuals is almost always denoted as either S or SE. You'll notice right here we have an S. That is your standard deviation of the residuals right there. So all we have to do is find them and now interpret them. So first thing I need to know is what's X and Y. Okay. So we look down here at this table because it's not telling me what X and Y is in the problem. Over here, it's not telling me anything. But recall that whatever you have for your LSRL, remember this is the LSRL right here. That's your X variable. So if I underline down their units, that's X. And we can see that it's the number of components repaired or replaced. So my guess is the idea here is you're plugging in how many are repaired, and then that's going to predict the length of the call. Okay. Another way to tell is we have the dependent variable up here. Dependent variable is minutes, dependent is your Y. So that's another dead giveaway in this table that the X variable is going to be the number of components repaired and the Y variable is going to be minutes. So remember, dependent is your Y. This is not always going to be there. Okay, that's not always going to be there. In this example, it is. It will not always be there. Just be aware of that. Sometimes it is, sometimes it is not. So now I know X and Y, I can do my R squared interpretation. Okay. So R squared is 98.7. So we'd write 98.7% of the, I'll use variability this time, and Y is the minutes, or in the length of the call is explained. Could also be accounted by or accounted for. So we'll do that this time. Is accounted for by the linear relationship with X, which is number of was it components? Number of components repaired. All right. 98.7% of the variability length of the call is accounted for by linear relation to the number of components repaired. So we have R squared done. The last thing we need is S. Remember, S is the average distance the actual Y's are from the predicted, and S is 5.392. Y, the units are minutes because it's the length of the call, and it also says the dependent variable is minutes. So we would say the average distance, the actual lengths of the call are from the predicted lengths of the call is 5.392. I'll put minutes on there. Average distance, the actual lengths of the call are from the predicted lengths of the call is 5.392 minutes. I mean, that's it. It's really just plugging in the variables into the equation, or the sentences that I wrote out in the beginning. We can look at one more. This will be the last example. So kind of ignore the directions. This one, it says a college professor collected data on a stratified random sample of 116 Savannah sparrows at Kent Island. The weight and wing length were obtained from the birds in the nests that were reduced, controlled, or enlarged. Okay, so we can look at our thing. Once again, this is a different table. It is not looking exactly the same. But notice right here, we have that same sort of predictor coefficient thing. So that's the LSRL. And from the LSRL, I know my X variable is going to be wing length. So if X is wing length, then Y must be the weight. So I think the idea is you're measuring your wing length, you're trying to predict how heavy they are. It's much easier to measure the length of something as the weight of a bird. So we can do this. We can easily do this. So let's look at that. We have our R squared. This is R squared adjusted, ignore it, and then there's your S. So we have the two statistics. We know our X, we know our Y. We can just quickly type in and interpret these. So for the coefficient determination, we would say 61.4% of the variability in Y, which we said is weight, is explained by the linear relationship with wait life. So perhaps we should say it's about birds, but that's good enough. And the last one we have is S. S is there. So then interpret the standard deviation of the residuals, or S, or whatever you want to call it. We would say the average distance, the actual wing lengths are from the predicted wing lengths is 1.39959 millimeters. And there you have it. You're done. We interpreted R squared and S again. So that's all I have for you in this video. Hopefully you followed how to find the stuff and figured out how to interpret them. The next one, we're going to be looking at confidence intervals and hypothesis testing. So I will see you then.